Hi everyone. In this lecture we're going to look at another method for computing volumes of solids. Let's just recall what we did last time. We are interested in computing the volume of a solid. Let's say the solid obtained by taking this region and revolving it around the y-axis. Now what did we do? Well, we did this method where we looked at all these cross-sectional areas. So we took the solid and we sliced it up into a bunch of cross-sections. We imagined them all laid on top of one another. We found the areas for each of these cross-sections, and then we integrated. In this case, the way I'm gesturing, we're going to integrate along the y-axis of all these cross-sectional areas. And that gives us the volume. Now in the particular case where we're looking at an object created by revolving a region around an axis, to get these cross-sectional areas that are all stacked on top of one another, we took a slice that was perpendicular to the axis of rotation, so that when we revolve it, we end up getting something that looks like this, which we called a washer. So this is a side perspective, of course, of this. It's actually a circle with an inner circle removed, which we call an annulus. Or we're loosely calling a washer from the hardware store. You get these things, they go around screws. Now, what do we need in order to work out the area of this washer? Well, we're imagining a whole bunch of washers as we go from y equals 0 all the way up to y equals 4. So at this particular y value, what do we need to work out the area of this washer, which we're going to call A of y. What is the area of this washer? How do we compute that? Well, we need two things. We need to know the area of the big circle, or the disk, the area of the big disk, and the area of the small disk that removed from it. The area of the disk just requires us to know what the radius is. So what we need to know is the radius of the big disk and the radius of the small disk. We called these things the outer radius and the inner radius for the washer method. So we can answer this question, what is the area? It is pi times the outer radius squared, r sub 0, or r sub o squared, r outer squared, minus the area of the inner disk removed, which is pi ri squared. Now what we need is that both of these things to be written as functions of y. That's what we'd like. So I'm going to ask a question. Can we write these things as functions of y? Given we're at height y, can we get the inner and outer radii? Well, those would require knowing these values on the x-axis. So can we get x in terms of y here? X in terms of y. Can I get x in terms of y for both of those things? That's really the question. Are these functions of y? Well, that involves getting x in terms of y. Can we do that? Well, let's see. What would it take? Well, if I was to get these two sides of this curve in terms of y, so x in terms of y, it would involve writing this piece as x is some function of y, and we would have to do the same thing for the other piece. X is some function of y. And so what does that mean? Well, it means taking our original curve, y equals 3x squared minus x cubed, and trying to write it, because that's what this thing is, y is equal to 3x squared minus x cubed. That's the full curve to begin with. Can I take that and break off these two expressions? Break off the right and the left-hand side? Well, that would involve solving this equation for any given y value, solving for x. That's a cubic equation. We'd expect to have 3 possible solutions for x. We're going to have to try to pick off the 2 that represent each of these slices, or each of these sides. That's a difficult problem. In this particular example, really difficult problem. In some examples, it may be impossible to actually do this. So what can we do instead? We're trapped here. Using the washer method, we're trapped in the sense that it's going to be hard for us to try to take the original curve and split it off into two expressions where now we've got x as a function of y for both of those halves. So what do? Well, here's where we exercise our imaginations. We're going to look at this region. We're going to revolve it around the y-axis, constructing this solid. How can we do this? How can we get a procedure for computing the volume, is what I meant to say. So how can we do that? Well, imagine this. Rather than taking a horizontal slice, so that the object that it makes when we revolve it is a washer, let's take a vertical slice, so that the object we create when we revolve it is a cylinder. So in terms of our diagram over here, we've got a cylinder that's sitting inside it. And we could do this for various different x values. I'll draw a couple of them over here. Do another cylinder. And in fact, we do this for every x value between a and b, and we're going to get a whole bunch of concentric cylinders that fill up the solid. Okay, so now what do? Well, now if we imagine that we know the areas, the surface areas of all these cylinders, all these concentric cylinders, then integrating over all of those areas is going to give us the volume. Much like we did with the stacking. We stacked up all of these areas for the washer method, stack them all up, integrate over all those areas, we get the volume. In this case, we're looking at concentric cylinders, and we're going to integrate over all of these concentric cylinders to get the volume. So that's the idea. What does it mean? It means we need to know the area of the cylinder. So what we're going to call the cylinder is C sub x, just to indicate that it's determined by the position x that we draw the line segment at. The line segment we've called L sub x. Just in the purposes of the discussion, it's not really going to be used very much in practice, just other than the fact that we just need a name for it. Now we want to come up with the area of this cylinder. This is a cylinder that, it's got a surface area here, and we want to find the surface area of the cylinder. So how do we get that? Well, let's just draw it again here. And how do we get the surface area of the cylinder? Well, let's imagine that this is a label on a can. So we've got a cylindrical can, we got this paper label on it, we slice down, vertically downward the label, and we peel it off. And what kind of shape results? When we peel off the label, we get a rectangle. That's the key to getting the surface area of the cylinder. So realize that when we cut and peel, we get a rectangle. Notice that the height of this rectangle is just the height of the original cylinder. That's going to be a key ingredient in our work. We need to know the height of this arbitrary cylinder, this one at position x. What is its height? Its height is going to be f of x in this particular case. What else do we need to know? We need to know the radius. Why do we need to know the radius? Well, the height gives us, the height of the cylinder gives us the height of the rectangle. What does the radius of the cylinder give us? Well, when we slice and unroll, the circumference of the top now becomes the length of the rectangle. What's the circumference of a circle? Well, that's 2 pi times the radius. So this is 2 pi times x. And this is 2 pi times the radius. That's where it's coming from. And so that's 2 pi times x in this case. This was the height of the cylinder, which is f of x in this case. So we unroll, we get this rectangle. What is the area of this rectangle? Depends on what position you took your vertical slice at, what x position. So this is really dependent on x, but it's just going to be base times height. 2 pi x times f of x. That's the surface area of one rectangle at position x. Now we imagine we do this for every x value between a and b, construct all these cylinders, nestle them inside one another. They fill up the entire volume of the object. So we're going to integrate over all of these areas to get the volume. And so that's what we do here. We integrate over all of the areas to get the volume. In this particular case, the area was given by x, 2 pi x f of x, so that's why there's a 2 pi out front. Came from this length of the rectangle, 2 pi times the radius. So this x sitting here is radius, and this f of x sitting here, that was the height of the cylinder. This was the radius of the cylinder. And this is the key. Not the formula. 2 pi integral of x f of x dx. We're going to see that that formula doesn't always give us the result that we want. We may be integrating or we may be revolving around the y-axis, in which case it doesn't make sense to integrate with respect to x in this way. So we may revolve around another line altogether. So this one was specific for the case of revolving around the y-axis of a region trapped between a function and the x-axis. But in general, what we just need to do is multiply 2 pi times the integral of the radius of the cylinder times the height of the cylinder. And we're going to see that is the result we're using in all our examples to come. So let's do a bunch of examples. This is coming back to that first one where we saw that the washer method wasn't going to help us very much. So let's use the method of cylindrical shells. Always a good idea to sketch an arbitrary shell so that you can start collecting your elements that you need in order to piece together the integral. So there's our arbitrary slice that's at position x. So this immediately tells me that I'm going to be integrating over all of these different x values. X goes from 0 to 3. That'll sweep out, these vertical lines will sweep out the region. So those are my limits of integration, and x is my variable of integration. So what do I need to know? I need to know the radius. What's the radius of this cylinder at position x? Well, it's the distance from this vertical line, the line we're revolving, around the axes of rotation. We're revolving around the y-axis, so its distance is going to be just x. What's the height? Well, at position x, the height of that cylinder is just given by the height of that point. And that's going to be given by the function value. That is f of x, which in this case is 3x squared minus x cubed. So now we can write down what the volume is. The volume is 2 pi times the integral from 0 to 3. We're doing this with respect to x, of the radius of all these cylinders times the height of all these cylinders. And so this is 2 pi times the integral 0 to 3 of x, 3x squared minus x cubed dx. So there's our integral that represents the volume of the solid. Now we can go ahead and work it out. It's the integral from 0 to 3 of 3x cubed minus x to the 4th dx, which is 2 pi times the integral. Well, now I can anti-differentiate. So this is 3/4 x to the 4th minus 1/5 x to the 5th from 0 to 3. So this becomes 2 pi times, pop the 3 in. There's a 3 times a 3 to the 4th, so that's a 3 to the 5th over 4 minus 3 to the 5th over 5. Or in other words, it's 2 pi times, well, I can bring the 3 to the 5th out of both of them. And I'm left with a 1/4 minus a 1/5. So 1/4, that's the same thing as 5/20 minus 4/20, so that's 1/20. 1/20, there's a 2 out front, so that leaves me with a 10 on the bottom. And so there's our result. And we can write this as 243 pi by 10. There's the volume of the resulting solid. So again, key thing to keep in mind, setting up this integral which represents the volume, we took 2 pi times the radius of the cylinder and multiplied by the height of the cylinder at position x. And then we integrated all over those. So the radius and the height, that's the key thing to keep in mind here. Let's look at another example. Here we've got a sphere of radius b, and we've cut out a cylinder, bored a hole through it of radius a, so we've removed a cylinder from the middle of it. What is the volume of the resulting object? This ball with this sort of cylindrical, this cylinder pulled out of the middle, this horrible out of the middle of it. What is the result? Well, what I've done here is I've just redrawn the upper hemisphere, because if I compute the volume of just the upper hemisphere with this hole removed, then I can multiply by 2 to get the volume of the whole thing. I'm just going to focus on the upper hemisphere. The region we're revolving is this little segment here trapped between this portion of the circle and this vertical line, and we're revolving it around the y-axis. That'll sweep out this upper hemisphere with the hole removed. Now, to do the shell method, we're going to take an arbitrary slice. This will be at position x. X ranges anywhere between a and b, so we already know our variable of integration and our limits of integration. Now we just have to find expressions for radius and height. So there's our cylinder. And I need to know the radius and the height. What's my radius? The radius is the distance from the vertical line segment I've chosen and the axis of rotation. So that's going to be x in this case. That's our radius of our cylinder. What's our height? Well, given the x value, I need to know the y value of that point. How do I find the y value of that point? I'm not given any equations in the actual question. Well, here we have to realize that we're looking at a sphere, a hemisphere, and I've drawn a cross-section of it. So this would be a circle, a semicircle of radius b, where I've sort of removed the top of it. So this one is a circle, or at least a portion of a circle, of radius b. So we have an equation for that. It's x squared plus y squared is equal to b squared. Or in other words, we're interested in just the upper portion of it, so I can solve for y. Y is equal to positive square root of b squared minus x squared. So that's the curve there. Y is equal to square root of b squared minus x squared. So what's the height? The height is square root of b squared minus x squared. So we've got our height, we've got our radius, so we've got all the ingredients we need. The volume is going to be the integral, well, 2 pi times the integral. As x ranges from a to b, the radius times the height. So now we're left with computing this integral. How do we do this? How do we compute this integral? Well, one thing I notice is that what's under the square root sign, its derivative is out front. What's under the square root sign is a quadratic. The derivative would be linear, and that linear thing is out front. So this is a prime candidate for doing a substitution on. So we're going to go b squared minus x squared. So du is equal to negative 2x dx. And so we got 2 pi times the integral from, okay, so now I do a substitution. I'm going to put everything in terms of u, but I also need my limits of integration in terms of u. It's a good idea to switch them now for the definite integral. So my old limits of integration, where x equals b was the upper limit, x equals a was the lower limit. What are our new limits of integration? What are our new values of u? Well, when x was b, u is b squared minus b squared, so that's 0. When x is a, u is b squared minus a squared. So those are my limits of integration, b squared minus a squared to 0. Notice the order that I've put my limits of integration in. U equals 0 is the limit of integration that corresponds to x equals b. X equals b was the upper limit, so u equals 0 is my new upper limit of integration. X equals a was my lower limit, so u equals b squared minus a is my new lower limit. I didn't switch the order of my limits of integration for u because u is smaller than b squared minus a squared. Keep them in the same order because they correspond to the respective upper and lower limits of integration. So keep that order in mind. You have to put the new upper limit where the old upper limit was. What else do we have? X dx. X dx is -1/2 du. And the square root of b squared minus a squared, that's the square root of u. So there's our new integral. Now at this stage, I can realize that there's a negative sign in the integrand, and I can absorb that into the integral while switching the limits of integration. And that 1/2 can come out front and cancel with the 2 out there. Oh, there's one more thing that I should be careful of. What am I computing the volume of? Well, right now I'm working the volume of the hemisphere. I really want the volume of the whole thing. So I could either indicate this right now by saying I'm going to multiply by 2 this quantity that comes out, in which case this would be a 4. Or I could have done this integral and then multiply by 2 at the end. But I'm going to multiply by 2 here and just indicate why. So this is the upper solid volume. And this multiplied by 2 is for the whole volume. Okay, so I just wanted to point that out. So now the 1/2 comes out front. 4 times 1/2 is 2. This negative sign, as we just started saying, the negative sign I'm going to absorb into the integral and switch the limits of integration. And there's a root u du still here. Now I can integrate this. This is 2 pi, so I anti-differentiate. The square root of u anti-differentiates to u to the 3/2, 2/3. And that's going from 0 to b squared minus a squared. And now we pop the limits of integration in. 2 times 2/3, so that's 4/3 pi times b squared minus a squared to the 3/2. And so there is the volume of the full sphere with that hole removed, that core hole removed from the middle of it. In this last example, we're going to look at the same region revolved around various different axes just to see how the integral changes, which represents the volume of the resulting solid. So in this first case, we're revolving it around the y-axis, and it's the region trapped between these two curves. So here is a typical slice. Maybe that'll be at our particular x value. What does this slice look like when we revolve it? Remember, I took the slice parallel to the axis of rotation, so that means our slice is going to give us a cylinder when it's revolved. So there is our cylinder. What I need to know is the radius of this cylinder. What's the radius of this cylinder? It's the distance the line is from the axis of rotation, and that is distance x. What is the height of the cylinder? Well, the height at position x would be the difference between the heights of these 2 points. Do we know the heights of those 2 points? Well, I need to know their heights in terms of x. What's the height of, well, let's do the lower point. The height of the lower point, well, that's on the curve y equals x cubed. So the height of this point here would be x cubed. So I'm just going to bring these things out. The height of the lower point is x cubed. So maybe I'll draw that in here. So that's x cubed. What's the height of the upper point? Well, it lives on that upper curve. The upper curve, x and y are related by x equals y squared. So if I know the x value, then I know that y is equal to root x. So that height would be root x of that upper point. And so the height of this line segment, or the length of the line segment, or the height of the cylinder, is the square root of x minus x cubed. Okay, so now we can work out the volume. What's the volume? The volume is 2 pi times the integral as those vertical line segments sweep out the entire region. So the vertical line segments sweep out the entire region. That means they go from 0 all the way out to 1. So 0 to 1 are the x values that are swept out times the radius times the height, square root of x minus x cubed. So again, really important to note here. This is radius, that's where that's coming from, and this expression is height of that cylinder at position x. So there's our volume. It's just represented by this integral. We work out the integral, we've got the volume. So now we're into integration mode, calculating an integral. So x times root of x, that's x to the 3/2. X times x cubed, that's negative x to the 4th dx. Now I can anti-differentiate. This is x to the 5/2, 2/5 is our new coefficient, and then 1/5 x to the 5th. And that's from 0 to 1. So the integral then becomes 2/5 minus 1/5, or 1/5 of 2 pi. So 2 pi by 5. And there's our result, 2 pi by 5. So again, draw an arbitrary cylinder at a position x. Make sure you think about which x values sweep out the entire region. In this case, it was 0 to 1. Work out the radius and the height, and then throw them all together in that integral. The integral of 2 pi times the radius times the height. Let's look at the next example. Now we're revolving around the x-axis. So we're going to take our cross-section, our line segment, parallel to the axis of rotation. That gives us our cylinder. Now this is at some arbitrary position y. So we already know at this stage that we're integrating with respect to y. And the line segments that sweep out the region go from y equals 0 all the way up to y equals 1. So we already know our limits of integration and our variable of integration. That's important because I need to know this height of the cylinder, and I need to know what variable I want to express it in terms of. And y is my variable that I'm using. So I need to get this height expressed in terms of y. I also need to know the radius. The radius is going to be this distance here. That's our radius. So what do we have? Well, the radius, how far away is this line segment from the axis of rotation? Well, it's just a distance y from the axis of rotation. How about the height? Well, I need to know the x values of these 2 points. Because if I can get the x values of those 2 points, I can take the right point x value minus the left point x value and get the length of that line segment, which is the height of the cylinder. So given a y value, can I find the corresponding x value gives this point on the blue curve? Yeah, it tells me that y and x are related in this way. Y is x cubed, or in other words, x is the cubed root of y. So that value there would be cubed root of y. What about this value over here? Well, if x is y squared, that means if I know the y value, I can get the x value by just squaring the y value. So that is y squared down there. And so what is the height? It's the cubed root of y minus y squared. And so that means that our volume is equal to 2 pi times the integral. Y goes from 0 to 1. The radius is y. The height of the cylinder is cubed root of y minus y squared dy. So again, this is radius, and this expression is height. And now we can work out the integral to get the value of the volume. So this is 2 pi times the integral from 0 to 1, y to the 1/3, so cubed root of y is y to the 1/3, times y is 1/3 plus 3/3, so that's y to the 4/3 minus y cubed dy. Now I can anti-differentiate each piece using the power rule. So this is y to the 7/3, 3/7 minus 1/4 y to the 4th, and that's from 0 to 1. So this is 2 pi times 3/7 minus 1/4. 5 pi by 14. Okay. So let's look at this next example. Now instead of revolving around the x-axis or the y-axis, we're revolving around the line x equals 1. So here's x equals 1. That's the thing we're revolving around. We're going to use the shell method. So I'm going to sketch a typical slice parallel to the axes of rotation and draw the resulting cylinder we get. I still need those two bits of information. I need to know the radius and I need to know the height. So what is our radius in this case? What is our radius? Well, let's think, what variable are we going to write this thing in terms of? Remember, the variable of integration can be determined by how you've sketched your individual slice. Our slice is completely determined by its x value. It's a vertical slice. It's determined by its x value. As x goes from 0 to 1, these vertical slices sweep out the entire region. So it's completely determined by its x value. So everything's going to be in terms of x now. Height's in terms of x, radius in terms of x. What's our radius? Well, the radius is the distance from this vertical line segment to the axis of rotation. The vertical line segment's at position x. The axis of rotation is at position 1, so the radius is going to be 1 minus x. What's our height? Our height is going to be the difference in the heights of these 2 points. So what are the heights of those 2 points? Well, given an x value, I need to know the y value of the lower point in terms of x. And I can get that right from the equation. Given the x value, y is equal to x cubed. So that's x cubed. What about for the upper curve? Given an x value, what's the y value? Well, x is y squared, so y must be square root of x. And so our height is equal to square root of x minus x cubed. So our volume is given by the integral. Well, it's 2 pi times the integral, 2 pi times the integral from 0 to 1 of the radius, 1 minus x, times the height, square root of x minus x cubed dx. And that's, again, just realize that the key fact I'm using here is that that's radius and this is height. I'm integrating 2 pi times the radius times the height. So again, if you think back to the formula that we wrote down, we had the 2 pi times the integral of x f of x dx. That doesn't always hold. We're just starting to see some examples now where we just really have to think, what is the radius of the cylinder? What is the height of the cylinder? That's what really matters, not this formula. This formula doesn't really matter. It's what is the radius of the cylinder? What is the height of the cylinder? You integrate 2 pi times the radius times the height. You're integrating over all of the areas of these rectangles which were coming about as the surface area of those cylinders. That's the key here. So let's go ahead and do this integral. This is 2 pi times the integral from 0 to 1. I'm going to expand this out so I just get a bunch of powers of x. So that's x to the 1/2. So 1 times root x, I'm just writing root x as x to the 1/2. 1 times negative x cubed, that's negative x cubed. Negative x times root x, so that's negative x to the 1/2 plus 2/2, so that's 3/2. Negative x times negative x cubed is positive x to the 4th. And dx. So that's the thing we're going to integrate. X to the 1/2, the integral is x to the 3/2, 2/3 minus 1/4 x to the 4th minus 2/5 x to the 5/2 plus 1/5 x to the 5th. That's from 0 to 1. So plugging the limits of integration in, we get 2/3 minus 1/4 minus 2/5 plus 1/5. And that is equal to 13 pi by 30. So there is the value of our volume. Okay, so we've seen some various examples of revolving regions around different axes. The key thing is to try to keep in mind, how can I compute the radius and the height in terms of the variable of integration, in terms of the variable that you're integrating with respect to. Now I just want to make one comment. We've now got these two methods, the washer method and the shell method. How do we know which one to use? Well, it all depends on the bounding curves for the region you're interested in and whether it's easiest to use x as a variable or y as a variable. Once you've decided the variable of integration you're going to use, then you want to decide, am I going to use cylindrical shells or the washer method? Well, if the strip that you've taken, the little line segment you've taken, because you can work out its length and its position in terms of the variable that you want, if it's parallel to the axis of rotation, when you revolve it, it's going to make a shell. So that makes the shell method, or uses the method of cylindrical shells. If it's perpendicular to the axis of rotation, then it creates a washer. So that means it's the washer method you're going to use. So you just want to look at the relationship between your line segment you've drawn and whether it's parallel or perpendicular to your axis of rotation. All right, thanks very much for watching, and we'll see you again next time.